Welcome back! In the previous lectures, we have discussed the important component in a PV system used for power conversion, the inverter. In this video, I will present a general overview of different inverter topologies used in PV systems. The learning objective of this video lecture is to recognize and understand the pros and cons of the different inverter topologies, like a central inverter, a module inverter, microinverter, a string inverter, multi-string inverter, and a team inverter. So let's start with the simplest architecture employed in PV systems, the central inverter's installation. In this topology, the PV modules are connected in strings leading into an increased system voltage, and then the strings are connected in parallel, forming a PV array which is connected to one central inverter. This configuration is mostly employed in very large-scale PV power plants where the central inverter performs maximum power point tracking and converts the DC electric power into a three-phase AC power. When more than one string is connected in parallel and significant difference in the irradiance from string to string are expected, blocking diodes are required to prevent current circulation between the strings. Concerning the inverter, two main topologies are generally used, either a single DC to three-phase converter or three separate single-phase inverters working synchronously with a phase difference of 120 degrees each. Such a centralized configuration with all the PV modules connected in a single array offers the lowest specific costs, which is the cost per kilowatt peak of installed power. And finally, it's important to notice that this is a quite established architecture, which means it is reliable enough to work for a couple of decades. In spite of their simplicity and low specific cost, central inverter systems suffer from some disadvantages. First, we have that due to the layout of the system, a large amount of power is carried over considerable distances using DC wiring. Therefore, the engineer has to carefully choose the type and thickness of DC wires, because this can cause safety issues related to fault DC currents and the need for thick cable insulation, and special circuit breakers can lead to significant cost increase. Another drawback is that all strings are operated at the same power point, which might not match the maximum power point of each string and hence be problematic in a very large installation. Imagine, for example, a cloud casting its shadow on part of the installation for a couple of seconds. The result is a high imbalance in the power generated by the modules that causes mismatch losses and reduces the overall system output. A third drawback is the low flexibility and expandability of the system. As the central inverter is designed to work with a specific installed peak power, its maximum input power is limited, and so is the number of modules that the array can accommodate. Lastly, since we have to use blocking diodes in each string to prevent current circulation, then we have to consider also their additional power losses. A very different architecture is that of the module inverters, also called microinverters, because they are just as big as the junction box. These inverters operate directly on one or several PV modules and have power ratings of several hundreds of watts. Because of the low voltage rating of the PV module, these inverters often require a two-stage power conversion. So in the first stage, the DC voltage is boosted to the required value, and then it's inverted to an AC in the second stage. The output voltage has to be compatible with the grid to which they are connected by means of an AC bus. In order to avoid phase imbalance, all the microinverters are connected together with special additional units, depending on the brand, which control the output signals of each inverter. As I mentioned, microinverters are very small, and this is because inside they have a high frequency transformer, which is cheaper and smaller compared to the main transformer. Additionally, it provides full galvanic isolation, which enhances the system flexibility and makes this concept easily expandable. So for example, if after a couple of years we want to install more modules, we can just buy additional microinverters and a new power unit that controls all of them. Let's now see the drawbacks of such a system, because all these advantages come at a price. Since these inverters are mounted on the backside of a PV module, their embodiment has to be very sturdy in order to operate in harsh conditions such as high temperature and large daily and seasonal temperature variations. Again, special attention should be put on safety issues related to cabling to avoid that animals bite the cables, resulting in conduction failures. Another disadvantage is that the PV module voltage is much lower than the output AC voltage. Therefore, the DC-DC conversion has to considerably boost the voltage, and this has a detrimental effect on their inverter efficiency. Also, if you have a very large number of modules, then it's no longer economically interesting because the specific costs are the highest of all the inverter topologies. The next architecture features string inverters, which combine the advantages of the central and the module integrated concept with little trade-off. So here the modules are connected in series to form a string, like for the central inverter concept, with a power rating of up to 5 to 6 kilowatt peak in one-phase configurations, and the open circuit voltage are up to 1 kilovolts, which already exposes one disadvantage of this topology, since high DC voltages require special consideration, as in case of the central inverter architecture. Here this issue is even more important because string inverters are usually being installed in households or in office buildings without designated support structures or increased safety requirements. The protection of the system also requires special consideration with emphasis on proper DC cabling. Another important characteristic is that if each string has its own maximum power point tracker, then each string can independently operate at its maximum power point. Thus, partially shading and hotspots will occur only in modules within the same string. Also, because no strings are connected in parallel, there is no need for blocking diodes as in the case of central inverter, and as a consequence, the losses associated with these diodes are eliminated. The multi-string inverters architecture is a hybrid between central and string inverters. Here, an optimizer box is attached to every string and it contains a maximum power point tracker and a DC-DC converter. The DC to AC conversion instead is shifted to a power electronic unit just next to the grid. So all the string optimizers boxes are connected in parallel to each other and then to the central inverter. It is important to note that if the DC input voltage of the central inverter is outside the specified input range, then the current is altered such that the voltage falls within the acceptable range again. So the main advantages of this architecture is that every string can operate at its maximum power point, and the optimizers operate at voltages close to the voltage of the string. Hence, the DC-DC conversion is very efficient and the optimizers consume very little power. In this architecture, we can easily add additional strings, but not only you have to be careful that the inverter can handle the additional power input, but also you have to buy an additional DC-DC converter, which is a drawback. Finally, based on the string concept, we have the team inverters configuration, suitable for places with variable meteorological conditions. Basically, it's a combination of several string inverters working with the team concept to reduce the overall losses, as any power electronic converter is designed such that its maximum efficiency is near full load. The concept of team inverter is that each string is connected to a bus that is activated or not depending on the amount of power that the PV modules are generating. So at very low irradiation, the complete PV array is connected to a single inverter, while with increasing solar irradiation, more inverters are being connected, dividing the PV array into smaller units until every string inverter operates close to its rated power. In this mode, every string operates independently with its own maximum power point tracker. Of course, with this master-slave fashion, we need to have an additional intelligent circuit that basically makes a round robin in the usage of all these inverters in order not always use the same inverter. To sum up, in this video we have seen 5 main installation concepts for solar inverters. The first and easiest architecture is the central inverter, which connects in parallel different strings directly to one single 3-phase inverter. The second type features module inverters. Here some microinverters are directly connected to one or a few PV panels. As we have seen, this design makes the system more flexible and easy to expand. On the other hand, the cost can become prohibitive if there is a high number of modules. Next, we had a look at a system concept which utilizes string inverters. In this case, each string of panels in series is connected to one single inverter, and then several inverters are connected in parallel between them. The fourth architecture is multi-string inverter. In this case, each string of PV panels is connected to a DC-DC converter that adapts the voltage level to meet the requirements of a single central inverter. Here the DC to DC converters are all in parallel. The last concept involves team inverters. What happens in this case is that each string is connected to a bus that is activated or not depending on the power intake from the PV modules. As we said, we need additional intelligent control to apply this architecture, which translates it into a more complexity. It is important to say that each of the presented concepts is valid, but it has to be accurately chosen depending on the system project and the system costs. Next week, we will discuss many other components that may be part of a PV system, like battery, charge controllers, cables. In addition, we will look at the loads and the electricity grid. So, see you in the next video lecture.